Now that we have done similar polygons, we're going to apply that directly to similar triangles. And we're going to prove similarity, and we're also going to use to find what's called indirect measurements. So on this warm up, we have a stick is placed vertically at point B. So clearly you see there's a mistake right there. That should be B. And the top of the stick is in line with the top of the tree. So those 2 points there, when you are looking up. So as you look up from A, we see that we have a line of sight, which means the top of the tree is directly behind the top of the stick. Line of sight is what we call that, or collinear as well. We're told that we are, that point is 3 meters from the stick, and we know that we're 30 meters from the tree. So those are things that you can measure. Just measure those 3 things. 1 here, 2 here, measure this, 3 here. And now we can calculate to find the height of the tree. So today what we're going to do is figure out why we're allowed to set this up, but I do want to see first off a setup. What we did here is logically we can set this one up, and this isn't the only way, and we're just saying one way. So if we put the heights on the top and the lengths or the distance away from the object, and next if this one is talking about the stick and this one is talking about the tree. Now, as long as you keep your categories organized like this, it doesn't matter where you place everything. Somebody else could have set it up differently. Good, so in this setup, again, perfectly logical, but what we're doing here is comparing the distance compared to the distance. So this one is the stick to the tree, and this one is the height of the stick to the height of the tree. All of these, logically, will end up giving you the same, as long as you don't cross-pollinate. Don't say the height of the stick compared to the distance to the tree. That would be different, wrong comparisons. So it doesn't matter which one you cross-multiply and solve, or if you just said this one here multiplies by 10 going this way, so that has to multiply by 10 going that way, or you divide by 2/3 going this way, or multiply by 2/3, so you multiply by 2/3 there. So whichever way you think about it, in the end, the answer is 20 feet, or meters, excuse me, meters tall. How tall is it? Today what we're going to look at is similar polygons, or similar triangles. So what we have here is a postulate, which means it's unproven. We just accept it as true. It's called the AA similarity postulate, and it reads as follows. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the 2 triangles are similar. So in this case over here, angle K is congruent to angle Y, and this angle J is congruent to this angle X. So because of that, the 2 triangles are congruent, and it doesn't actually matter the order in which you write it, as long as the first one corresponds with the second one, like this. Since J matches with X, I went ahead and made sure that those both came first. K matches with Y, so I put those second. Notice what you can also just do. I just took one of the angles, converted it to a triangle, because those are already in proper form. All right, so down below here, do we have enough information to determine if these are similar or not? Actually, the real question is, are they similar or not? So we can actually say definitely no or definitely yes. So let's look here. Here's a 92 and a 92. So those 2 are congruent, here and here. So it seems that we're missing an angle. So when we use the triangle sum theorem, so that means this one here is 31 degrees, but clearly we see they do not match right there. Those 2 don't match. So the answer is no, because, or not similar, because 31 degrees does not equal 41 degrees. C is 55 here. We actually don't even need the other one. 48 matches with 48. And 55 matches with 55, so the answer is yes, they are similar. And the reason for it, if they asked you, was angle-angle similarity. Okay. Now the last one here. This one is 43, right there. So 1 pair of angles, but we don't know another pair of angles. So this one will be not enough información. We just don't know. So there are two other ways to prove similarity, triangle similarity. And this first one is called side-angle-side similarity. If an angle of one triangle is congruent to an angle of a second triangle, and the sides that include the two angles, hence the side-angle-side, are proportional. So here's the key difference. We're talking about proportional instead of congruence. Then the triangles are similar. So notice here, there's no proportional markings. They just compared AB to QR, and then they compared AC to QS. And as long as those ratios are the same, then number one, you'll find the scale factor, and number two, you see that they're proportional. And we're given that the angles are congruent as well, the included angles inside here and here. So notice, so far, to prove triangle similarity, we have angle-angle similarity. We have side-angle-side similarity. And then the last one here, if the corresponding sides of two triangles are proportional, side, 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 then the two triangles are similar, side, side, side. So quick question, why not this one? And why not this one? Talk real quick with your neighbor. We don't know these ones because the angle-angle supersedes. Angle-angle similarity, angle-angle similarity. I don't need anything to know about sides. Angle-angle is enough. Why not HL? Because HL is actually side, side, side because of the Pythagorean theorem. So HL is actually side, side, side by Pythagorean theorem. So we actually don't ever need that one as well. So we have three different methods to prove triangle similarity. So let's take a gander at 6, 7, and 8. 6 is going to be not enough information because we're either missing congruent angles to make it angle-angle, or we're missing, in this case, also congruent sides. That's just coincidence, though. And that would make it for side-angle-side. No, but we couldn't even do side-angle-side on this one. So, all right, so let's see over here. Proportionally, let's set things up. 5 looks like it's going to compare to the 10. And let's see if it's equal. I'm going to put a question mark there. 14 and 28. Two ways to do this. You can cross-multiply and get the same number. Or 28, thank you. Or you can reduce both of these. If I reduce both, I get 1/2 equals 1/2. 1/2. And so that's a check. They are in proportion. And then lastly, the angle in between. So the reason for this is side-angle-side similarity. Over here, we do our comparisons, and we see that every single ratio, 15 compared to 30, does that equal 13 compared to 26? And then this 13 compared to this 26. And since the scale factor is 1 to 2 for each one, then the answer is yes by side, side, side. 26, thanks. But we'll look at this. Thales was an ancient philosopher familiar with similar triangles. And one story about him says that he found the height of a pyramid, by measuring its shadow and his own shadow at the same time. So if a person is 5 feet tall, what's the height of the pyramid from this diagram? Okay, so why do we know the triangles are similar, first off? Why are the triangles similar? Well, so this has to be the same angle as this. That's called the elevation, the angle of elevation of the sun. No matter where you're standing, the angle of elevation will be the same. That's the nature of parallel lines. You could also argue the sun's rays are parallel like this. So then you could say essentially corresponding angles. And then second, when we're talking about upright, 90 degrees right there, it's safe to assume 90 degrees on both of those. So by angle-angle, the two triangles are congruent. So now let's set it up. The length of the shadow is 318 relative to the length of the person's shadow. And then the height of the person, I'll put in the denominator there, and the height of the pyramid, put there. Again, it doesn't matter your setup as long as your setup is logical. Now when you cross multiply and solve, we'll get an approximate height. So this one is exactly 265, but again, measurements could be off, so approximately is probably a good symbol there. And the last thing I wanted to show you here was these last two practical problems. Explain why the triangles are similar, then find the distance represented by x. So let's look at this first one here. So note how one can set this up is making some marks on the side of the river on which you are standing. So if you make those marks here, and then just clearly choose a point, maybe there's a tree over on this side that you are straight across from, and then stand here and notice here, from this point to the tree is collinear. So when you look, boom, whatever this is, a flag or a tree, is going to be in the way over there. So all you now have to do is first off determine what's congruent. Well, by vertical angles, those are congruent. By right angles are congruent. Those are congruent. So we know the two triangles are similar by angle-angle similarity. So with that in mind, all we have to do is set up the proportion. Notice that the distance away from the river is going to be similar to the distance across the river, or proportional, so divided by x there. And then the distance along the shore compared to the distance along the shore. Now, if you'd like, you can go ahead and reduce here, which I will, and then cross multiply and solve. So here I get 240 equals 5x. So x is going to be 48. So what's that mean? How far across is the river? So what does that mean? So that means the distance across the river is 48 feet, which just goes to show that this is not to scale at all, because this looks isosceles to me. And just to finish up over here, notice what you can do is setting up a mirror right there, and if you look down from here and you look down and you see the top of the flagpole from there, you've now created similar triangles. Why? By angle-angle similarity. And here it's safe to assume that those are 90 degrees. So by angle-angle similarity, the two triangles are congruent. So all you have to do now is set up and simplify. So the distance away from the mirror here is 4.5 compared to the distance away from the mirror here is 12. And the height, it says height is 6 feet, so that's going to be 6 feet right there. And then the height x feet there. Again, cross multiplying, canceling, whatever, and we just solve to get 16 feet. Again, not drawn to scale, because to me this flag looks significantly higher. But in terms of number, it does make sense. Notice here, 4.5 here and 12 here, so this is nearly triple the size here. So if you triple this, you get 18. So 16 is a close number there. It's just not drawn to scale here.